Welcome to this webinar presented by the IET's Anglian Coastal Local Network, which represents members in Norfolk and Suffolk. Welcome also to folks from other parts of the UK and indeed globally. I'm delighted to welcome you all. I'm Kevin Foster and I'm chairman of the Anglian Coastal IET Local Network, and I'll be your host for this evening. I'm delighted to introduce our speaker, Stephen Eaves. Stephen is the CEO and founder of VaultServer, a venture-funded technology company in East Greenwich, Rhode Island, USA. Since 2014, VaultServer's ability to deploy touch-safe, high-power electricity in a safe, data-enabled digital format has led to successful installations in nearly 1,000 premier venues, including hotels, office buildings, NFL stadiums, and indoor vertical farms. Steve has more than 20 years experience in founding and managing energy-related startup companies. Prior to VaultServer in 2006, Steve founded Modular Energy Devices, a lithium-ion battery company acquired by Enosys in 2011. Modular Energy Devices became a leading supplier of lithium-ion batteries to the US telecommunications industry, with thousands of installations worldwide. From 2000 to 2006, Stephen founded and served as president of Eaves Devices, and they developed power electronics and energy control systems for the B-2 bomber, ships, submarines, satellites, and the International Space Station. He's authored or co-authored numerous industry and academic peer-reviewed papers related to energy industry, and that have appeared in respected academic journals and media outlets such as Newsweek and the Washington Post. And they have been referenced by corporations, governments, and economic development organizations. Steve has more than 30 patents issued or pending related to energy storage and power conversion. He graduated with a Bachelor of Science degree in electrical engineering from the University of Connecticut in 1987 and is an Air Force veteran. So Steve, over to you.
Hello, everybody. Just going to share my screen here. Thank you, Kevin. Thank you, IET members. It's a pleasure to be here. Hello, everybody. I'm going to talk about a new technology for electricity transmission, and also more generally talk about something that we call digital transformation. And we'll get into both those subjects and how digital electricity applies to digital transformation. So as many of you know that are involved in the industry, the world is transforming in many business sectors, whether it's communications or indoor farming or buildings. More and more digital devices are being put in and deployed. And those devices, they rely on two things. They rely on a data connection, and they rely on a source of electrical power. The data side has been evolving exponentially over the last decades, but power distribution has remained relatively the same. It's rigid, it's relatively difficult and expensive to install, and it's inherently dangerous. So what digital electricity does is address that factor and try to bring a form of electricity that's as flexible as the digital devices that are being served. So a comparison of a conventional AC system, there's a lot of traditional protection devices. Here you're looking at a US installation that requires hard conduit runs in commercial installations, and a lot of conventional devices such as circuit breakers and arc fault and ground fault detection. A digital electricity system has the power capabilities of traditional AC power, but in that format that I'm describing, in a new format, it's been rendered both safe from a touch perspective, but also fire. So one way of looking at it is that it brings the power capabilities of AC power distribution, but it installs like what you'd be familiar with as Ethernet cable or USB cable, which is a limited energy source distribution system. And I'll talk about that a little bit, the technical details that make that happen. An overall description of the architecture is a conventional source is brought in, whether it's an AC or DC power source or stored energy. It could be a battery or solar array or conventional AC power. And from left to right, that's brought into a device that we call a transmitter. And the transmitter takes that conventional power and it breaks it up into what we call energy packet format. So the protocol that we use internally is packet energy transfer. Digital electricity is a brand name for that protocol. And one way of looking at this is if you can imagine conventional distribution of electricity in your house, your home, or your business now, it's in a continuous stream as it comes from an outlet. And in that continuous format, if the voltage is high enough, it can be dangerous, because of the exposure of your body to electrical current from that voltage. But one way to render that safe is to break it up into small pieces. So if it was water, we would take a stream of water and break it up into billions of small droplets, where each one of those droplets was safe in itself. And by tracking that small unit of energy across the transmission lines and making sure it gets to the remote location, we can ensure that it went to the right place, that it went to a receiver on your right side of the screen here. And that receiver then converts back to analog format, back to regular electricity. If it goes somewhere else, if it goes into a human body or into a source of fuel for ignition for a fire, then we know that that very small unit of energy didn't get to the right place. On the bottom of the screen here, you're looking at the general format that we use for transmission. It's a small burst of electrical energy, a pulse of electrical current, and then a period of what we call the data component, which is only 500 microseconds in duration. And during that data period, that's where we're verifying using digital signal processing that energy component made it correctly to the other side. A little bit more detail on the energy packet. So the energy packet is essentially a high voltage. The voltage is actually, if you looked at it with an oscilloscope, you would see it would look very much like DC electricity. There's this area where data transfer and analysis occurs in the data component, where if you had a very good scope and you zoomed in on it, you would see this little dithering pattern that would be data transfer during that period. But if you were looking at the oscilloscope from a current standpoint, the current would be in discrete pieces, electrical current. You would see current flow and then stop as we entered the data period. And that is essentially the energy component of the packet. So in that period, the lines are electrically isolated from both the transmitter and receiver source. So the only thing that's holding the voltage up in that data component period is the inherent capacitance of the lines and some internal capacitance that's in the receiver and transmitter components. During the data component, we transfer both safety information in analog and digital format, and we also can send monitoring or control information back and forth between transmitters and receivers. In a very advanced system that you'll see in the future, we'll track units of energy very discreetly from one specific source to another specific load, so that we're moving specific types of power from one location to another. So these systems right now out in the industry are predominantly volt server systems, but I will say that in the US that there is a draft standard being opened up with Underwriters Laboratory and also in the National Electric Code. There's others coming into the industry which will expand the use of this type of technology in the market. But as I mentioned, it's well embedded in systems in North America, but also Europe predominantly. And we have, as Kevin mentioned, about 1,000 large installations. I'll talk here for a moment about electrical safety and how digital electricity, being a high voltage technology, achieves the safety levels that I'm talking about here. So especially for the engineers on the line, one of the first questions we get is when we send really high amounts of power through thin cable, the first thing that's asked is, who are you trying to fool with this? We can, in the format of a Ethernet cable, where predominantly now you might transfer up to about 90 watts at the end of the line, these systems can transfer about 1.4 kilowatts. And although they're used in communication systems, they're also used in industrial applications, with some of the larger installations reaching 1 megawatt of installed power or more. So I'm showing a chart here that has a column here that's regular sort of AC or DC power, and then a digital electricity comparison. For years now, we've had protection on AC electricity for high current through the circuit breaker. And in the 70s, the ground fault interrupter was introduced here in the US in the National Electric Code. And then it wasn't until the late 1990s that arc fault was introduced into code to handle that particular aspect of an electrical arc in the circuit. But there's two other very important faults that haven't been addressed by traditional electricity formats. And one of them is what's called a resistive fault, and the other is touch fault. So a resistive fault is if you have a poor connection, or what's called a glowing fault in the circuit, that can reach pretty high levels of power and cause a fire in the system. And it's very difficult to detect that fault. It's not something that shows up as high current. It's not high enough current to trip the circuit breaker, and there's really no ground fault involved. It's just a poor connection. So the systems in packet energy transfer, because we're comparing very minute amounts of electrical energy in these packets, we can tell whether a single packet hasn't made it to the end of the line. And that's in elements of millijoules that I'm talking about. So digital electricity can detect resistive faults in the line, and which is extremely important when you're installing using what in the US what's called Class 2 or Article 725 installation practices, which are the same practices as Ethernet cable. Finally, another important aspect of safety detection that's not addressed in conventional technologies is touch fault. So if you have a cord, like say you're using an insulated device like a vacuum cleaner that has a plastic shell, there's really just two wires in the cord. There is no ground wire coming back from a double insulated device. If you strip back the insulation on that power cord, you'll expose the power conductors. In the US, there's a hot and a common, as we call it. And if you touch those two wires, then you'll be shocked. The conventional devices, whether it's arc fault or ground fault or circuit breakers, the shock value in terms of current, even if you are at very dangerous levels of electrical current through your body, aren't detectable by those devices. The closest thing you might imagine is a ground fault detector, but ground fault detectors are looking for a sort of sneak path through a ground, like a faucet or something like that. And there is no ground path in a double insulated device. And even with a ground fault protected circuit, if you touch the hot and the neutral, it won't be detected by ground fault. Ground fault only detects from the hot to earth. So moving on in relation to transmission of high voltages, one way to look at this is when you're sending energy in very discrete components that are very short in duration. As you saw, the packet is about 2 milliseconds in duration. You can have an exposure of elevated voltage, but as long as it's very short in duration, it doesn't fall into a region of safety that's dangerous to humans. When I was growing up, there was a little gadget that you would put in your hand that you could shock somebody with. It was a gag gift, and that's essentially what it was. It was very high voltage, but very low, short duration pulse. So as a static charge that's on a doorknob, could be tens of thousands of volts that's accumulated on that location. But when you get the shock from that doorknob, it's not dangerous because of the duration and the content of energy. These systems that I'm talking about here are much less than that. They don't hurt you like a doorknob would surprise you, but you can feel them if you touch the wires. So here I'm showing a couple comparisons. I use some European measurements here. So you could look at the purple here in the yellow region. This is ELV, or band 1 voltage, as it would be described in the UK, which can extend to 120 volts DC. And to explain this chart a little bit, the lower axis is the body current that's formed. So it extends from 0 to 10,000 milliamps on the bottom axis. And on the vertical axis is the duration of exposure. So in this little corner here in the lower left, that's a 10 millisecond exposure at 0.1 milliamps. So it's way in the safe region of DC1, which is all these regions here I'm pointing to, DC1, DC2, 3, and 4, are areas of exposure that have population numbers attached to them. So if you're exposed to those regions, you have higher and higher probability of cardiac fibrillation. So ELV, going back to ELV, is kind of in a yellow region. It hasn't entered into DC3, but it wouldn't be considered, I would say, safe. It's still in a questionable region. If you have, say, a weak heart or low skin resistance, it's still not a great spot to be. You can see here's plus or minus 190. This is a common communication powering system, remote communications. This has a fairly high exposure for line-to-line exposure. And then here's another very familiar, this sort of whitish dot is power over Ethernet, or 60 volts DC. It might also be in a similar region as 48 volt power and telecommunication systems. So here, what you have is digital electricity in this green area here is its exposure in terms of current is between 100 and 200 milliamps, but the duration is under 10 milliseconds. So by keeping the duration short, it's able to stay in the region of DC2, which is a safe exposure region for humans. A little bit more comparison information. So to give you an idea of what this type of power transmission means when it's used in, say, communication installations or using communication installation practices. The left bundle here is power over Ethernet. And these bundle sizes here are for if you had to transfer a really high amount of power, in this case with PoE, one of the extended 60 watt, you might call it 60 watt power over Ethernet transmission, the bundle size is pretty substantial. And you can get heating in the core of the bundle when they get this large. But with a digital electricity installation, the bundle gets very small. You can see that in relation to the size of a pen. But maybe more importantly, the heating in watts per linear foot is about a quarter of what it would be for 60 watt PoE in that bundle. So why do people use it? It has installation practices like communication cabling, carries a lot of power, goes really far. The technology is qualified to about 2 kilometers of range. And it can do that at substantial power levels. A little background for those that are very interested in how is one of these systems used in the field? How is it installed? This diagram here is talking about, this would be a classic installation, say for a communication system or an intelligent building. The transmitters look like little, not so little, I suppose. They look like computer servers. They're 2U in height. And the one I'm showing here is a 2U 19-inch rack installation. It's about 12 kilowatts in this unit, and you stack more and more units for higher levels of power. As I mentioned, in a big stadium, you might have 200 or 300 kilowatts of power installed for digital systems, and in an indoor vertical farm, they could exceed as high as 10 megawatts of installed power in one of the very large facilities. I try to give folks an idea of what the capabilities are here on the top. Here you can, with about 500 watts of transmission, you can go 220 meters on 18 gauge cable and 1100 meters on 14 gauge. And to get the full 2000 meter transmission, we usually do that on 12 gauge. And again, you have to reduce the power levels per pair as you go further and further in distance. But these 500 watt levels are fairly reflective of what many of the installations are out there. So I put in a few use cases here. So this is a stadium installation. So I did a little funny business with pictures here. I'm actually showing the transmitters here. This is Brave Stadium. It's another transmitter installation from another stadium, but it had a really nice picture, so I used it. And then the receivers look like this. This is a 48-volt receiver. You can see it installed in a hallway of the stadium where the players are walking by here. And this is 5G deployment. So a lot of systems now are migrating towards 5G, and a good part of our business at here at Volt Server is related to migrating towards 5G infrastructure. I'll play a little video here for folks to see. I'm going to kind of show you what it looks like in one of these stadium installations, and hopefully I'll get the screen sharing right. Okay, I am sharing right.
Football excitement is at a fever pitch here in Miami. The Chiefs and the Niners have worked all season for this one moment.
But keep in mind, Verizon's network engineers have been hard at work for 2 years to ensure the network is ready for the big game.
Preparing for the Super Bowl, it takes a lot of people from design, construction.
So I'll stop there so you kind of see what an installation looks like in a large communications infrastructure project. And these are, the transmitter units, very much like the diagram I showed you earlier. These are terminal blocks and many times over voltage protection for outdoor systems. And then you could see behind this, there's more racks of stuff. So these racks keep going into the picture. And then there's multiple rooms that have these systems. And then the cables go up through the infrastructure. You could see this green cable on the left of the screen. That's the cable that we're using to transmit there. And then it goes up through data channels. So in a conventional AC in one of these stadiums, you would be using for power from a central location. You would be using conventional practices in North America, which are a lot of core boring and conduit work, and it's relatively slow, rigid, and expensive. But in this case, the data channels and the power channels have been converged, going back to digital convergence. So a common team with common skill sets is pulling the cable. Many times the fiber and the copper are in the same cable jacket. So the power is going with the fiber, and it goes up through the cable trays and then out to the remote location, which might be 1,000 feet away. The advantage is it's very fast, and they avoid, especially in US markets, in a typical stadium installation, they might avoid 30 to 60,000 linear feet of conduit installation, and put all this in the existing trays in the facility. This is a good installation. Here's an installation that is an intelligent building application. So this is this very cool hotel in Fort Worth, Texas, USA. And it's a connected, what we call a connected building. So everything in the hotel room is controllable. They're all IoT devices. And when the guests are not in the room, the systems in the room are automatically brought down to a low energy state to save energy. So everything, there's blinds and thermostats and water temperature and lighting are automatically controlled. And when there's no guest in the room, the shades come down, the thermostats turn down, the hot water temperatures are manipulated. Everything is brought to a point of where there's less energy use in the room. And I'll play a little video here so you can see what this is like.
Sinclair Hotel is probably the first truly connected commercial building in North America. The customer experience at Sinclair is very important to us. I think in this day and age, people are looking for experiences. So we are working with Intel and learning about AI, IoT, and data. AI is the future. When you're in your room, it's like having a virtual assistant that you can communicate with. You can get any information you want about the surroundings, about any restaurants in the area. These are little things, but they're very important to guests. From guest experience to business operations, the latest in IoT technology matters. This building is connected. The entire building, the entire lighting system, the entire motorized window blinds and roller shades. Your rooms are very integrated with all these endpoints that are connected on this network. Intel's role in Sinclair development matters because they bring a lot of knowledge about data. I'm already very grateful for Intel leading this whole effort by us. And they are putting us on the map with other major companies and showing what we have been able to do here. By going to this technology, we are seeing anywhere from 35 to 40% energy savings. 35% is very significant. That's a third of power consumption saved. And if all buildings do that, that means a third less power plants out there, a third less greenhouse gases out there. So, I mean, this is a trickle-down effect that can have some very big reverberations all the way down. Intel helps us see the small things which make a big difference, and that has a big impact on our business. My name is Farooq Aslam. When it comes to technology, everything matters.
So that's a connected hotel, and I promise you I'm not getting any commercial reimbursement from Intel. It's just a really great video that we use all the time. Our final application that I wanted to show today is indoor vertical farming. This is a really exciting space right now. So across the world, food production is starting to transform. And this is another example of digital transformation. It accelerated during COVID-19 for us. And a lot of it had to do with labor shortages. During COVID-19, the borders in the US, in many places in the world, they closed down. And so in the US, a lot of migrant labor is used to farm in outdoor farming. And so using indoor farming, it's the production is all year round, and the production indoors can be 30 to 50 times the rate of outdoor farming. It uses a lot less water. It doesn't use chemicals, or it doesn't use pesticides, I should say, or any artificial ways of controlling insects or anything like that. I should say that it can use chemicals and chemical fertilizers, but this one here that I'm going to show is actually organic in its production. And the other thing that happened during COVID is that in areas like Canada, because of border closures on countries that depended on food imports, there was sort of a big scare at the governmental level of they looked around and said, hey, if this happens again, if it gets bad enough, we can run out of food if shipments aren't allowed to transfer. So that resulted in a relatively pretty big push in development and investment in indoor vertical farming, or sometimes it's called controlled environmental agriculture. So I'll show a little video here. This one is food. There's also a lot of cannabis installations that are out there now as cannabis begins legalizing across the planet. I should mention that before it gets started, that the downside of indoor vertical farming, as you might have also seen in some other areas like crypto mining, is the power consumption. So because there's actually no sunlight used, it uses all artificial lighting, there's a ton of energy that's used in these processes. But there's a movement in the industry in this particular installation to supplement it with power. So as strange as it sounds, what you're looking at is a picture of a 1 megawatt indoor farming facility, and then a 1 megawatt solar facility that's outside of it sitting next to it. It sounds like a ridiculous proposition, but the aspects of control in these facilities are the predominant driving factor for value. So although the sun is quote free, it's really hard to control. And the expense in using the sun is the aspect of you can't control when the harvest happens, market conditions, weather, and also just managing a greenhouse when the sun is coming in on some days and some days it's not is extremely difficult. So as strange as it sounds, the facilities actually harvest the sun into electrical energy and then convert it into artificial lighting. So I'll let the video go now.
Everything that we do at HardyFresh is based around 5 core principles: safety, quality, consistency, availability, and sustainability. We use the most innovative energy efficiency devices and techniques in our production facility. Devices like VoltServer that allow us to have greater control over environmental conditions while using less electricity. We also power our facility with a 1.1 megawatt solar facility that allows us to decarbonize the entire process of growing produce. The challenge for us at HardyFresh is to figure out how to serve and meet the expectations of our customers and to evolve with customer tastes and change and customer demands. When we're thinking about how to design the facility and how to build it, the first thing we considered was, what does it mean in terms of our operational control of the farm? What VoltServer clearly provided was a superior opportunity to have control of our lights and some of our other IT infrastructure. When we made the decision to incorporate VoltServer into our design, it was really all about having a digital end-to-end fault-protected technology that would allow us to integrate seamlessly into our automation controls. But there were a number of other important advantages that were associated with higher fidelity control. Included that VoltServer is safer for our workers, and therefore we could commit to them that they were working in an inherently wet-rated environment, meaning that they didn't have to worry about shorts or faults in our electrical system that might impact them as they were working on the crop. Also, VoltServer is just the most energy efficient way for us to manage large numbers of lights in a facility like this. And so when we thought about it from a design perspective, it was clear that we'd have better controls, a safer environment, and achieve energy efficiency outcomes that were important to us as a company.
Conventional farming is very, very, very difficult. Difficult because you cannot control the weather. And here,
I'll stop it there. It goes on for a while. But that's another example of digital convergence or transformation. This time in farming, we looked at communications, we looked at buildings and farming, and of course, in every other aspect of our lives, things are digitally transforming. And today, what that I talked about today is how one of the big elements of digital transformation is energy transfer to those digital devices. And the digital electricity, we believe, is the ideal method to do that. So that's it. That's all I had. Kevin, I'll send it back to you. Thank you.
Thanks very much, Steve. Great presentation, and I think it's sort of the innovation around here is very interesting, because it does start you thinking about power distribution, and lots of other kind of use cases come to mind, and I'm sure there are going to be quite a few questions around this. Certainly when I first discovered this capability and this new way of thinking about electricity distribution, it really did. It's quite transformative. So thank you for going through the technology, and thank you for sort of indicating that standards work is beginning to advance on this type of electricity distribution. And I think it certainly is a lot of food for thought, and I'm sure we'll have a lot of questions, and I can see there are at least 14 stacked up there. So without further ado, I'm going to hand over to my colleague Ian Buxton, who's going to look at the questions and present them to you, or ask them to you, Steve. So over to you, Ian.
Okay, thank you, Kevin. As Kevin said, there's a number of questions. Some of them are around use cases, some of them are around the more technical aspects. There was one, though, from Kira N that's around about the history of this thing. And he or she said, isn't this effectively just a differential protection scheme that was first demonstrated in 1901 using telegraphs? So I don't know if you know the history of it, Steve, but maybe you could give an answer to that.
I have no idea. Like a differential protection scheme. It sounds like that might be dealing with leakage currents, or some methodology around that. I would say it's not likely. Back then they had the signal processing that was necessary to execute this type of technology. Here, what we're sending is extremely brief, discrete, quantized pulses of electricity combined with data. Not like power over Ethernet, where it's an analog low voltage electricity format with data riding on top of it. In this case, the energy is actually packetized. It stops and waits, and it's verified to a very finite level that that unit of energy transfers to a remote device. So like a ground fault interrupter is a good example. Maybe that's a good example of a differential technology where that you're looking for the same amount of current leaving one wire has to return through the proper wire coming back, and they use a Hall effect device or other current sensor to make sure that the net current is zero. If it goes to another place like the ground, then that would be a fault. But that would be an analog. We're not discretely tracking actual energy content and interacting with a load device. So I guess that's as best I could do, because I don't really recognize that earlier technology.
That's okay. That's fine. Whilst we're on the subject of what really digital electricity is, there's a couple of questions there which are around are your packets compatible with existing network routers? And I suppose a more basic thing, which you may have just kind of answered, but how is the electricity digital? So maybe you could just kind of explain that a little bit further, perhaps.
Yeah, I think we've been, at least many of us have been accustomed to the definition of digital as being sort of data transfer, and it does do that. So, you know, and I'll have to admit or relent that the digital electricity is a brand name. You know, the technical protocol that we run under is called packet energy transfer. But yeah, I think I did mention that a digital thing is just a unit, something that's been broken up into a discrete unit. Even going back to mechanical mechanisms were digital when I think a good example might be a radio that had, early radios had push buttons that you pushed a discrete button and it set you to a channel. That would be an example of a digital device. And we're using the term sort of according to its definition, just that we're sending electricity in discrete quantized units that are tracked.
That's fine. Thanks, Steve. This question is around, can we deliver digital electricity without cables? So I don't know quite what they're getting at, whether it's wireless or perhaps, but maybe you know.
I think so. Yeah, we get that question a lot. It is a cable-based system. It's very difficult to transfer high amounts of power wirelessly. And many of us probably here are in that field. You know, so RF transfer, for example, probably the best method or the closest method that might meet that requirement is microwave transfer. There's some low frequency devices like wireless charging of your phone. They work really well, but over short distances. But as you extend that phone further and further away, the field expands, and the amount of energy in that field is sort of just the area that is in the surface. It turns into a big ball, and you need a giant ball to get a little bit of energy to a surface that might be 50 feet away or a mile. So it's really hard to transfer high amounts of power. Microwave is an interesting way that it's been done. It's been demonstrated. Still, it takes a lot. The efficiencies are very poor compared to wire transfer. And you have this sort of problem of this really high energy beam of microwaves shooting from one place to another.
Thank you. A question from James Guyton. Could you just tell us a little bit more about the data portion in the energy packet? Is it used for power negotiation, detecting faults, as you mentioned? Can it also be used as a data channel for the application?
We do use it as a data channel for the application. It's a low bandwidth transfer. So it's used for monitoring control in our most advanced projects. But I should say that we have layers of communication. So the primary safety features of the technology are done, they're backed up by analog as well. So we're analyzing that area in the data component area, also with analog means as well as digital. So if we do lose communication, it always defaults to a safe spot. I will also say that there was only a limited amount of time, so I couldn't talk about communications in full, but we also have the ability to ride high-speed data on the same copper lines, much in the way that Power over Ethernet does it. So, you know, those lower speed packets are moving on the wires, and then riding on that is high speed, you know, 1 gigabit per second Ethernet. But our most common installation is fiber, you know, because fiber goes a long way. Ethernet goes about 100 meters, as many of you know, but fiber travels very well with our technology format because we can go kilometers and get a lot of power at the end of the line.
Okay, thank you. Question from Kira N, who obviously wants to read a bit more, I think. Have you published any of this technology in any of the IE or IET peer-reviewed journals?
Yeah, there's a couple papers out there that were picked up from conferences. We're fairly new. We're just now getting into that IEEE conferences and things like that. We do have a substantial engineering group, but we've been focused mostly on we're venture funded. And so we've been focused primarily on getting out there, gaining revenue and applications. So there's really not much like IEEE paper stuff out there.
Okay, thank you. A question from an anonymous person. He says, sorry if I missed this, but in the event of any cable damage or disconnection between the transmitter and receiver whilst in use, does the transmitter shut down? Does the transmitter monitor the loads drawn from the receiver and therefore can thereby dynamic management depending upon the application loads? So,
yeah, yep, I get that one. So yes, it shuts down if it can't validate, well, a lot of things, either the cable or the receiver, many things are being looked at, but if it can't validate that it has a proper transmission circuit, then it immediately shuts down. And yes, we do monitor remote load at the receiver section. So the software overlay on the system is, so in some applications, you might have emergency backup and the software is monitoring all those channels, and there's a set of rules that says when there's a power outage, which channels are allocated power for how long, depending on the critical aspect of those loads.
thank you, Steve. A question from Anwar. Can you harness PV generated DC voltage without needing to convert to AC and then back to volt server DE pulse DC? If that makes sense.
Yes, yeah, that's a really interesting aspect of digital electricity. In a way, one way to look at it is there's a large movement to move to what's called DC building architectures, and that's where you don't convert. You stay at DC. And so you bring it into the building and never convert back to AC because, as many folks might know, that most modern devices are already DC inside, like a refrigerator or your TV, or this monitor behind me is internally powered by DC, and the AC is converted to DC immediately when it comes in. So as time goes on, what we expect is, the OEMs that we work with, we're slowly moving towards this, is that devices would be directly powered and never need AC and avoid those conversions.
Great, thank you. Another anonymous one, is digital electricity compatible with existing packaged energy systems such as EPS conduits? Does that mean anything to you?
I think it might be referring to different data that's out there in digital electricity systems. Yeah, so in the United States, because we're what's called a listed limited power source, it's not required to have the cabling inside of conduit in the United States. European rules are different. It's not always like that, but over my head here, for those that are watching, you can see it's just a data tray installation where, I don't know if I have some over my head. Oh, there's some conduit up there. If you're conventional electricity, you install like that. It's less expensive, particularly with data enabled devices, to use a tray architecture like that. I hopefully answered at least part of that question.
Thank you. Anwar is looking as if he's trying to identify another use case for you, because he asks, are you using it in theaters for stage lighting applications?
Yeah, that sounds very interesting. No, I don't think we have. We have a lot of strange applications, but I don't think that's one of them yet.
Okay, thank you. So another question from, oh, whoops, just shot off the screen. Let me get it back. Panagiotis, I hope I pronounced that name right. Is DE applicable only for small power consumptions, such as lights, IT, ELV systems, or can it supply big loads like motors, and maybe how?
Yeah, I'll answer that in a couple of ways. I mean, our current systems, an individual load, it's kind of about how many pairs that we want to bring out there. Our current systems are limited, nominally to about 500 watts per copper pair, but they can extend if if the distances are shorter and the gauge is enough, the diameter of the cable, then it's about 1,000 watts per pair. And to get larger loads, we parallel those together to then get a high load. But after a while, the amount of pairs gets kind of silly, and we don't serve that application very well. But that's mainly evolution in the product, not the technology. The technology has strangely, I guess, that the packet energy transfer protocol, it doesn't really care that much about how much current is flowing through there. It still maintains the same safety level, whether there's a kilowatt in that pair or 10 kilowatts or 100. We are limited by current standards to about 400 volts line to line, and the new National Electric Code section article that's being developed, and the UL stuff will also keep that limit. I think it will stay between 400 and 450 volts. And so whatever sort of loads that can be served at that voltage level is probably where it is right now until a new standard develops to go to higher voltage.
Okay, we've still got quite a few questions to go through. Another question actually from Panagiotis again. Does the DE replace building management systems performing all monitor and control actions through DE distribution?
Yeah, it could take care of anything that is lower bandwidth stuff, maybe in the, the thousands, the kilobaud region, not, megabit type transfer. But I should say that there's a lot of movement. Again, you have a common cable. It's important that a digital electricity system in standards in the US, you can't put high power like that in communications in the same cable or in the same sort of jacket or tray where they're right next to each other. So it's very easy with these systems to run one pair that has digital electricity in it, and the other pair or pairs could be fiber or power transfer. It could be Modbus or BACnet or Ethernet that goes along with it. So you'd have a long distance run that has plenty of power and also plenty of bandwidth in that case. But if it's low speed devices like sensing temperature, then what we call our inline communications, or the data that's in that packet, should be enough.
Okay, thank you. A question from Tim. Is it the case that communications are bi-directional, so that the absence of a receipt confirmation from the receiver will stop the transmitter sending further packets? And can the communications link be used for other purposes? I think you've probably partly answered part of that question.
Yeah. If we're in a data transfer situation, then yeah, the lack of response. So basically fail-safe type practices. And then, as I mentioned, that's one layer of safety. The other layer of safety is actually digital signal processing, the analog components that are happening during transfer. So they kind of reinforce each other.
Okay, a question from an anonymous member, but probably very relevant these days is cybersecurity a concern for DE ecosystems?
Yeah, it's always a concern. Our customers, we're in very critical systems, of course. When you see us in a stadium or something like that, those stadiums are also rallying points for extreme events like a tornado or something like that. So the communication systems are critical. And so, our front end has, I'm not an expert in security in my position, but our front end is, there's a computer in there that's using security protocols, and then the customers also have a firewall where they add additional security to that. But it's always a concern and always something that is tested by our customers that we have to address often.
Okay, thank you. There's a question more around the commercial aspects from Alex. How old is this tech? When was it first commercially deployed, and how rapidly has it spread?
We were first financed as a company, venture funded company in the end of 2013, and our first system started installing in the last part of 2014, and so it's been since 2014, and now the installations have increased to, as we mentioned, about 1,000 large installations, and each of those installations can have hundreds or thousands of circuits, of course. So there's quite a bit on the circuit level. There's a lot out there for a little company.
Okay. I'm just going through some of these other questions. There's a question from Jeff. This is quite a technical one, I think. Isn't this effectively PWM-DC with a load check in the space regarding max power capability from IEC 6047179, max current less than 10 milliseconds is 500 milliamps, to AC 4, possible irreversible effects at 336 volts and at 75% duty cycle, that corresponds to 126 watts. How is the higher power mentioned achieved? That's above I hope you understand some of that, Steve, but if not, we'll move on.
I'll take a shot at it. I mean, PWM is pulsing current, which we do pulse current. But a PWM system, I don't really know how it would know what's happening remotely in a transmission line in the movement of energy. The tracking of the amount of energy that goes out from the source then meets the load. I suppose there's a way that it could be called that, a PWM system. We don't PWM, it's a fixed duty cycle, I guess. And the 60479 reference, it might be that the question is coming from a continuous exposure. Yes, if you had a 75% duty cycle at 336 volts and continued that cycle, you would reach dangerous levels. But the detection happens in 1 or 2 packets, so it's less than 10 milliseconds exposure. The question also might relate to the seeing the voltage being continuous. Well, I'd also remind the folks on the call that the current is actually dropping to 0 between each one of those on periods. But the voltage does stay high, but it's only a small amount of energy in that data component for data transfer and analysis. So if you actually touch the lines during that time, that voltage disappears immediately, and the line will shut down.
Okay. There's a couple of questions related to the technology again. One of them is from an anonymous attendee, and maybe we're probably getting towards the end of the Q&A, so we'll do these and then perhaps we'll have time for one more. But are there any EMC issues associated with the technology? Came from that person, and then I saw one talking about how do you deal with the harmonics generated when you convert the DC packets to AC? I guess there's a relationship between those questions.
Yeah, I think that the how is, yes, they're discrete, but through management of the edges of the pulses, you can move the frequency content into acceptable regions for EMI. So the systems are, of course, tested, FCC Part 15 and CISPR for European requirements, and also there's additional tests that our customers put us through for very sensitive telecommunications applications. So they're installed. I guess one way of answering is through demonstration, that were installed in thousands of circuits that contain sensitive communication gear, and well, that's how we do it. We manage the edges of the pulses so that they don't interfere into the frequency regions that would interfere with communication systems.
Excellent, thank you. I think we're getting towards the end of our time, so maybe we'll make this perhaps just two questions just to finish, Steve, if you don't mind. The first one is from Harold, obviously an operational guy, because he asked, what about fault finding and repair for all these installations? I guess how difficult it is.
Well, it's certainly better than conventional powering systems. Each one of those circuits, down to a very minute level, is being tested and reported. So if there's an issue on any of the circuits, the software will pick up that issue and communicate the location down to the circuit level of where the problem is, what type of the problem, even to degrees of cable degradation, poor connections, anything like that. And that's, the customers are supplied with that information through their networks, their central networks. And if there is an issue in a circuit, they can even remotely light up that card, that transmission card, to let somebody know what circuit it is in the field physically, or on the receiver side.
Great. And perhaps the last one to finish with is, may not even have an answer to it, but I thought I'd ask it anyway. In a domestic context, this came from David Broster, by the way. In a domestic context, what is the minimum installation cost? It's probably one of those unanswerable questions, I would imagine.
Yeah, I'll avoid that question. I mean, we sell them because it's less costly than conventional ways in the places that we sell. Like you saw the farm or the hotel. If we're in a very conventional installation, for example, if there's already power there sitting right next to the device, and there's not special concerns about, smart, how smart the power is, or if it's data enabled, the building, then we don't make a lot of sense. But when the building is digitally connected and the distances are fair, like maybe more than 200 feet of distance from the transmitter, because you make up the value mostly on the transmission, simplification of the transmission system. That's where we start making sense, and folks are interested in buying it.
Okay, thanks very much, Steve. I think we'll leave it there and hand back to Kevin, who will finish off the presentation. But thank you for answering all the questions that you did. Thank you very much.
Thank you.
Thanks very much, Steve. Very, very thought-provoking presentation. I found it fascinating, and more I think about the innovation behind the principles, the more interesting it becomes, because I start thinking of more use cases and applications. And I know personally, I came across the Volt server technology when I was looking at remotely powering street cabinets for telecoms kind of applications. So, lots of copper pairs in the ground, supporting a segment of the power could actually be quite useful for powering street cabinets for fiber to the home deployment, or fiber to the extension points where you need a certain amount of power, and you maybe not you can't get fiber all the way. Maybe you can power extension technologies. So very interesting, and this is in my mind, it's electrical distribution with an inherent feedback control loop that makes it safe. So thank you, for presenting that and presenting the ideas behind it, because I think it does challenge the traditional thinking for power distribution. And so very much appreciate your time presenting there. looking at future events, I just want to highlight we've got an active program being put together for 2022 for the IET Anglian Coastal Local Network, and the first webinar in 2022 will be on the 13th of January. And that will be about is graphene the new silicon, from Leonid Ponomarenko from the University of Lancaster. So a fascinating look at graphene being the new silicon. Now, other details of future presentations will be on our community site. There's a link there. If you click on that link, it presents to the new IET environment, and you'll have to then just search for Anglian Coastal. If you search for Anglian Coastal amongst all the other local networks, you'll see our program of activities. So I do recommend registering for the 13th of January. So finally, on behalf of the IET Anglian Coastal Local Network, I'd like to thank Steve once again for his presentation, the time he took to put that together and to deliver it. And I'd like to thank the team who put on the webinar tonight. Very much appreciated. That concludes the webinar, and you may disconnect now. Thank you very much.